This is the geometry. Now in this case, we look at our problem properties. This is AC magnetics. This time I'm using 50 hertz. AC magnetics. This is the air region. This is the permeable region, in which case I give it the permeability of mu metal, which is roughly 10 to the 4. This is our coil. This is a primary 1 and primary 2, and this is the superconductor. In this case, I'm modeling the superconductor as a to solve a superconductor. This is not a multiply connected superconductor, and I'm just using the very small permeability to model a superconductor in this case. The edges of the model are at 0 vector potential, and we can extend these further out, but they shouldn't be. Most of the field is going to be constrained to the permeable region here. In fact, if we wanted, we could actually even assign 0 vector potential to the sides without influencing it too much. So we have a coupled circuit. In this case, the primary 1 and primary 2 are driven by an external voltage. And we can look at the solution. This time we have to resolve it. Okay, so there is some coupling of the flux through the magnetic circuit here. If we want to look at the current that's flowing in the primary, we have roughly 10 amperes in the primary here, and this would represent the unfaulted case. Now, if we want to see, in this case, for the faulted condition, I'm going to switch this to air, corresponding to the superconducting tube essentially in the normal state. Now, if we're doing the nonlinear VH characteristics, the problem is going to take a little bit longer here. We can see roughly what the solution will look like. Now, the scale here is different, so there's actually going to be a greater flux penetration in here. In fact, we can animate the solution, and you can see that, yes, there is quite a bit of flux penetration here. And this time the current in the primary is reduced significantly here down to roughly 0.1, roughly 2 orders of magnitude decrease